Hello and welcome to Mr. Linford's math course. In today's presentation, we're going to be discussing applications to polynomial multiplication. In particular, we're going to be talking about using these applications to solve real-world problems, while also using them to work with variable dimensions and different geometric problems. First, let's take a look at a situation where we can use polynomial multiplication to represent different dimensions and quantities. So in this problem, we're talking about different types of zooms that you can have with a camera. Now, I should mention there are different types of zooms out there. When you have a camera and you hit the zoom button, think about what happens. The lens of the camera extends outwards. Sometimes if you have different cameras, you can even have attached lenses to them. So you can buy different lenses and attach that. That's called an optical zoom. That's where the lens of the camera extends out from the camera. What we want to talk about is what's called a digital zoom. A digital zoom is what happens on your phone when you take a picture. So if you have a smartphone and you are going to take a photograph using the photo app, you basically will go and your phone will capture whatever image is on the screen, and let's say, I don't know, you're taking a picture of some scene. Let's say there's trees. That's a great drawing, I know. There's your friend waving in the distance, and I don't know, let's say there's the sun over here. And let's say you have all this image on your phone, and you want to zoom in. When you zoom in, and let's say you zoom in on just your friend waving, what your phone does is, because the lens on the camera on your phone doesn't extend out, what it does is your phone will crop in to this blue rectangle. It will delete everything else that's not in the rectangle. It'll crop it out. So we're just going to remove all of this. It'll crop all of this out. And then what it does is it blows this up to fit on your phone. So when you do a digital zoom, you're not actually physically zooming in or extending the lens. You're essentially cropping down an image to a smaller image and then taking that smaller image and blowing it up. Think about, and this might, be more so for older generation smartphones like the older iPhones or Androids, but especially whenever you would zoom in all the way on your phone and you go to take a picture, it would look very grainy, very pixely. And that's often because you're not really getting the most quality there. You're zooming in so far, you're cropping so much out, and you're taking such a small area and then blowing that up to fit on your phone. So that's the idea of what a digital zoom is. In this problem, we're taking a look at how we can understand this concept of digital zoom to better understand the area that's captured by a photograph. So let's read from here. Using a standard 3:2 aspect ratio for an iPhone camera, Mackenzie is attempting to take a picture of a scene that measures 12 feet long by 8 feet tall. So let's try to draw what's going on here. Mackenzie has an iPhone and is taking a picture. Now, let's pretend this is the phone screen. We're told that there's a 3:2 aspect ratio. What I should clarify with that is the aspect ratio means what are the dimensions to your photograph. So a 3:2 means for every 3 units one way, it's 2 units the other. So it's a rectangular photo. 3:2 is the standard aspect ratio for photographs and what the iPhone takes pictures in. Now, you probably know if you have a more recent iPhone generation, you can switch aspect ratios. In fact, you can manually change to a number of different aspect ratios. If you have social media, like for example Instagram, their aspect ratio was always 1:1, a square. That's why they have square photographs. But you can change the aspect ratios. Maybe you want one that's even a really thin, almost panoramic-like. That might be something like a 4:1 or a 5:2, whatever. The idea with this is that the aspect ratio just controls the dimensions to the photograph. It controls the ratio between the dimensions, I should say. Now, Mackenzie is taking this picture, and, well, let's see. Let's say this picture is of some mountains. Let's put a tree here in the foreground. And we got someone waving here. And, let's put a sun again right here. Okay, so here's the scene that Mackenzie's trying to photograph. Now, when she goes to photograph this, she's going to try to zoom in. Oh, and remember, this is 12 feet by 8 feet. And what I mean by 12 feet by 8 feet, I mean when you set this camera up, and if you open your phone, your camera feature on your phone, and you look from this corner here to this corner, right? As soon as you're barely visible here and barely visible in this corner, and you measured that distance, you would find 12 feet in length. Similarly, if you measured from this corner to this corner, and again, you were like, okay, when are we just in frame in the corners and just barely in frame in the top corner? That distance right there would be 8 feet. So this tells us what's the immediate focal area. What's the immediate area of space that's being captured? Now, we need to zoom in, and we're going to use a digital zoom. So let's say Mackenzie zooms in and wants just this picture of the person waving. So when we zoom in like this, what Mackenzie's phone is doing is cropping out all of this area. It's cropping out all of that space and deleting it. And what's left over is just this zoomed in area. So, when we zoom in, I should also point out, this doesn't change the aspect ratio. Imagine, when you zoom in on your phone, do you suddenly go from a rectangular picture to a square picture? No, that doesn't happen. Or when you zoom in, does your picture suddenly get very, very long and then very short, so it becomes very narrow rectangular? No, that doesn't happen either. When you zoom in or zoom out, it doesn't change the aspect ratio. It's still going to say the same general rectangular shape. So we want to set for us here this information. This will tell us how we crop the photo in. So first up, when you crop the photo, you remove X feet from the top and X feet from the bottom of the frame. So when you go in and crop this, you are moving in X feet from the top and X feet from the bottom. Additionally, you remove 1.5x feet from the left and the right ends of the frame. So when you crop in, you move in 1.5x and another 1.5x feet. So this is telling us how much we're moving in. okay? It tells us how much we move in when cropping out the frame, and this is just to keep everything in the same aspect ratio, okay? Your phone has to know how much to move in on each of the dimensions, so that way when you zoom in, you suddenly don't get, from one rectangular picture to this type of vertical rectangle, or you suddenly don't get a square image or anything like that. Okay, here's that situation. Here's what we've done. We started with an 8 by 12. And now we've ended up with this blue rectangle. We got this by moving in x here and x units here, as well as 1.5x units here and 1.5x units here. What we need to do for this problem is find the area of the blue zoomed in space. We need to find how much area is right here. So remember, area of a rectangle. How do we find that? How do we find area? Area is equal to the length times the width of the rectangle. So before we zoomed in, for this whole big rectangle here, before we zoomed in, we would say that the area was 12 by 8, which is 96 square feet. Okay, 96 square feet. But that's not what we want here. We want the area of the interior rectangle, that blue area. So how can we go about finding that? What I'd like you to do, take a minute, pause the video, and see what you can come up with. Think back, we need to find area for this blue rectangle, so what information do we need to know? Maybe start there, and then start thinking, how can we get that information? And then, when you're ready, we'll come back and take a look at your answer. All right, well, hopefully you had some time to work through this problem. What I've done here is I've redrawn the image, so we have a little bit maybe clearer of picture of what's going on. And let's remind ourselves, we're trying to find the area of this interior rectangle, this blue shaded rectangle. We know that originally the rectangle was 12 by 8, but we've then moved in this many units from the top and this many units from the bottom, and we moved in this many units from the right and this many units from the left. So the question now is, what is this interior rectangle? Well, think back. If we're trying to find the area of this rectangle, we need to know its length and its width. So that's a good place to start. How can we identify the length and the width of this rectangle? Well, remember, maybe let's start with the width here, or the height. We started with 8 feet, okay? So from here to here was 8 feet. But we moved in X units. And then we moved in from here, X units. So now, what is this leftover area of space? How long is that leftover piece of space? Maybe it would help if we put in some numbers to this. Let's practice with some numbers first. So remember, originally, from here to here, the measurements of this large rectangle, it was originally 8. But we moved in this much here and this much here. Let's say we moved in 1 foot and 1 foot. Okay? How much is left over here if we moved in 1 foot on one side and 1 foot on the other side? Well, hopefully you're saying 6 feet is left. I mean, think about it. We started with 8 feet in total, but you moved in 1 foot here. So we only had 7 feet left over. But then we moved in a foot here, So now we only have 6 feet left over. So that's how much space we would have left. Let's try another setup. Now let's try, instead of 1 foot, let's pretend we moved in 2 feet on each side. Okay? So how much space would we have left if we moved in 2 feet from the top and 2 feet from the bottom? Well, hopefully you're saying pretty quickly that it would be 4. Because if we had 8 feet in total, you move in 2 feet from the top, then we only have 6 feet left over. But if you move in 2 feet from here, we only have 4 feet left over. All right, let's try one more setup. Let's try, I don't know, let's try 3 and 3. Okay, so let's pretend we moved in 3 feet and 3 feet. So how much would be left over? So you have 8 feet in total, but you cut away 3 feet here. So whatever is left, well, that's 5 feet we have left. But you cut away 3 feet from here. So how much is left over? Well, it should just be 2 feet. Because if you started with 8 and you took away 3 from the top and 3 from the bottom, that means you've taken away 6 feet. So only 2 feet are left over. This is how we're finding how much space was left. Okay? Now let's say that the amount of space that was removed is unknown. Let's say it was x and x. Then how much is left over? Well, when you do things with variables, think about what you did with numbers. Let it guide you, okay? We would say, well, we started with 8 feet. So we started with 8, but then we're going to subtract away an x from the top, and, let me get some space here, we're going to subtract away an x from the bottom. So 8 minus x minus another x, that would be whatever's left over in the middle here. And you know what? We can probably rewrite that, can't we? Instead of 8 minus x, we could say that's 8 minus 2x. That right there is the width of this rectangle. That's how tall it is. We can say, okay, we know that this is now, instead of 8, it's 8 minus 2x. Now let's go ahead and try the length out. Let's try to find what that length is. So let me clear a little space here. Okay. We're going to do the same idea. We start with 12 feet, right? From here to here is 12 feet. But we've moved in a certain amount. We moved in 1.5x. And we moved in another 1.5x over here. So now we want to know what's left over in the middle. How much length of space is left over? Well, we can say that that area of space left over for the length is, well, it's 12, and then minus 1.5x. Oh, but we have to minus another 1.5x. So negative 1.5x and negative 1.5x, that's just 3x. And there you go. That's the length. 12 minus 1.5x minus another 1.5x. That's the same as 12 minus 3x. So here's your length. And then the width would be 8 minus the 2x's. Now we have a way of representing the area of space for this blue rectangle. We have a way of representing its area. Notice, what is the area dependent on? X. We don't know how much we've zoomed in here, do we? That's okay. We don't know exactly how much. What we're saying is we're having a way of representing it, okay? Once you know what X is, then you can figure out the area. But for now, we're just going to represent it by a formula. So let's go ahead and multiply this out. Let's try the box method for this. Let's see, 8 and a negative 2x. And then over here, 12 and a negative 3x. So let's multiply this all out. 8 times 12 is 96. 12 times negative 2 is, negative 24x. Negative 3x and 8x is negative 24x. And negative 2x and negative 3x is positive 6x squared. So our answer for the area, when we multiply these polynomials out, is 6x squared. Negative 24x and negative 24x makes negative 48x plus 96. So this is just the product of this, right? These two formulas, they're the exact same thing. One's just multiplied out. So we have a formula for the area of this interior rectangle here, okay? That's what this work was to show us. It tells us when you know how much you've zoomed in, like whatever x is here, how much you removed from the top, you're able to figure out the whole area of the rectangle using this formula. And so let's go ahead and pretend like we know how much we've zoomed in. So let's say, let's say that when Mackenzie zooms in on the phone, we remove, let's say, 2 feet. Let's say we remove 2 feet from the top and 2 feet from the bottom. So if we remove 2 feet from the top and we remove 2 feet from the bottom, that means from the left we remove 3 feet, and from the right we remove 3 feet. Because 1.5 of 2 is 3, and 1.5 of 2 is 3. So we know how much we've moved in. Okay. Let's figure out what this interior area is going to be again. Now, you could say, well, if we know how much we moved in here, well, then we can justify how much was here, how much was here, and how much was here. We can figure out what this length is and this width is numerically, and then just multiply those. Or we can use the formula. I want to say let's try to use the formula here. So let's find the area when x is equal to 2. That would be 6, and let me write this a little neater. When x is equal to 2, that's going to be 6 times 2 squared minus 48 times 2. And then let's add on to that 96. So 6 times 2 squared is 4. Minus, well, let's see, 48 times 2. 40 and 40 is 80. 8 and 8 is 16. So 80 and 16 should make 96. And then I got to add another 96 to that. So what are we left over with? 6 times 4 is 24. And then negative 96 and positive 96 just cancel out. So we know that the area of that interior rectangle, when you cut out 2 feet from the top, will be 24 square feet. The benefit of having this particular formula is all you need to know is how much was removed from the top or how much was removed from the bottom. And so if you're going to try to figure out multiple areas, like if you're going to zoom in a few different times and you want the areas for all of those zoomed in rectangles, the formula can make it a bit faster and a bit easier for you to work with. You're able to see more specifically how cropping out certain distances affects the area. Let's continue on by now talking about a similar application. I don't know if many of you get things framed, but oftentimes people want to take very important documents like diplomas and degrees and certificates, or if they buy very special paintings and artwork, they want to take these things and get them framed. So at Michael's craft store, And no, I'm not sponsored by Michaels, just pointing that out. At this craft store, customers can get items matted and framed at the custom framing department. What they do is they take the item that the person wants, the frame that they want to put it in, and the foam matting that goes around the item, and they fit it all together. So when you go to Michaels, you will pick out, they have different trims for frames, they have different colors for matting, and you basically say, I want this mat and this frame, and they have to basically assemble the frame for you. They have to take the different pieces of the frame. They have to take the matting, cut it around, and they have to fit it to the photograph or the painting or the document, whatever, and they assemble it all into one picture frame for you. Now, to make the perfect fit, they got to be very careful with how much they cut of matting for the frame. And by the way, this can get kind of expensive. So how many, I don't know if it's done by square inches or square centimeters, but you're charged for how long, obviously for the frame. Sometimes there's a flat rate, but especially for the matting, how much, area of matting they have to use, how many square inches, square centimeters, whatever it is. However much they have to use, you get charged for that. So we want to know how much area of space is with that matting. Now, let's say Peter and Kata both have documents they want to get framed. So they go to Michael's to get these documents matted and framed, but unfortunately, to their dismay, they find that Mr. Linford is working behind the counter, and they know immediately they will need to do some math work. So, let's pretend I proceed to have them work with me to figure out how much area of space I will need for matting the documents. So let's try to draw a little picture of what's going on here. Let's pretend this is the frame boundary. So we have this frame here, and now let's go and let's say, okay, here is the document that we want to get framed. A little messy, but you get the idea. And then we're going to say, let's reserve this space around it to put matting. And what matting would do is it would just kind of act as like a little spacer in between the frame and the document itself. And they're different colors, so it kind of makes it look a little more dramatic or interesting. So that's the idea with the matting here. What we want to do is find the area of that matting. Now, keep in mind what we're saying here, the area of the matting. We don't want the area of the entire frame, meaning this is the area of the entire frame. We don't want all of this. We want just the matting. So if I removed all of this area, I'm kind of like punching a hole through the center of it. Let me try to get this drawn in a little neater. This red area, this kind of red rectangular space with a hole in the middle, that's what we want to find the area of, okay? So we need to find the area of just this matted boundary. That's kind of an irregular shape, isn't it? It looks like a rectangle, but it's got a hole in the middle of it, a rectangular hole right in the center. So what I want you to do is pause the video, take some time and kind of hypothesize to yourself, how could we go and find the area of this unusual shape? So pause the video, take some time to think about that, and we'll come back and look at some more specific values and how we can use this to help us find the area. All right, well, hopefully you had some time to work this through. So let's take a look at this next bit of information, and then let's see if we can use this to help kind of verify and get a better understanding of how we're going to go about finding the area of this red boundary. So if the documents that they're getting framed are 10 by 8, so 10 inches by 8 inches, find an expression to represent the area of the matting. So we want to know this area, all here. Now we're told how much area we are moving from the picture to get to the frame. So from the sides and from the top to the bottom, we add some space to get to where the frame is. From the bottom and the top, we move in x feet to get to the frame. From the left and the right, we move in 1.25x. So 1.25x. 1.25x. This is how much area of space we're moving from the left and the right to go from the picture to the edge of the frame. Maybe we can use some of these dimensions to help us out here. Now, when it comes to finding the area of an unusual shape, okay? So something especially that has a hole in the center. The trick for us is to find the total area. So we want to find the total area, the area of the larger shape. And then what we're going to do is we're going to subtract away the area of, I guess I'll say the area of the hole here. Okay? So this punched out area. This area of space that we don't need. When you do that, you'll be left with just this boundary area, okay? So let's see if we can use these dimensions to find the dimensions that we need to calculate the area of this boundary. So pause the video, take a couple minutes, and see if you can start to maybe evaluate what the total area would be of the boundary, or at least try to figure out how we can use these dimensions to set up the total area. All right, well, hopefully you had some time to work this problem through. What I'd like to do right now is take a look and try to really identify the dimensions of the different areas we have going on here. Now, remind yourselves that if you're trying to find the red boundary area here, you're really saying, okay, take all of this space, all of this total area, and subtract away this interior blue rectangle area. And whatever you're left with must just be the boundary. So we have two different areas to find here, the area of the blue, and we need the area of the total. Let's start with the area of the blue, because we know its dimensions. We know the length and the width of this rectangle. So I'm going to say that the area is 10 times 8. Okay, so that's 80. 80 square inches is the area for this interior blue rectangle. But how do we find what the total area is? Well, use a similar idea that we did before. We started with 10 inches. But we've added on to that 1.25x and 1.25x. Similarly, with the height of this rectangle, we started with 8, but then we added an x dimension here and an x dimension here. So let's see. The area should be, well, 10 plus 1.25x that I added to the left and 1.25x that we added to the right. Now, wait a minute, these are some like terms, so maybe we can add these together. So let's see, the area should be 10 plus 1.25 plus 1.25 should get me 2.5x. There's the length. That's how long all of this is. Now let's figure out the width, or the height here. Figure out how tall this is. So, I'm running out of space. So 2.5x. And then the height should be, well, we had 8. and we added an x to the top, and we added an x to the bottom. So really, it's 8 plus 2x. So here's our length, here's our height, or our width. And again, we don't know specifically these numbers because we don't know how much matting that they want for this picture. But once we figure out what x is, once we know how much height we want to have here, then we can go and start figuring out the rest of the area. All right, let's go ahead and multiply these together. We got a 10 and a 2.5x. And then we also have an 8 and a 2x. So let's see, 10 and 8 makes for 80. 10 times 2x is 20x. And now 2.5 times 8 should be, that's going to be a 20x. And 2.5x, let's see, 2.5x times 2x will give us 5x squared. So there is the total area, okay? This is a way of representing the total larger rectangle. It's 5x squared, and then with these like terms, we'll end up with plus 40x plus 80, and then don't forget we still want to subtract away an 80, which is the area of the interior, okay? So we've just multiplied this, and we're subtracting away this 80, so we can cancel those out, and we're left with 5x squared plus 40x. This is the formula to figure out how much area of matting we would need as the boundary. It's dependent on x. Once you know what you want this distance to be, you can find the rest of the area. So hopefully this is making sense to you and you're really comfortable working with this idea of representing these unknown quantities' dimensions. Because that's the big thing that we need to have here. We need to represent the dimensions not so much with a specific number, but with these unknown quantities. We need to say, what would it be if we didn't know what the values were, right? How is the length or the width being set up here? Let's go ahead now and try working more specifically with some geometric problems by just really trying to work with these unknown variable dimensions. Here we have a rectangle, and I'm asking you to find the area of this rectangle. Its length is 2x plus 1, and the width or the height is x minus 5. So go ahead, pause the video, give this a try, and then we'll come back and check your work. All right, well, hopefully this problem was easy for you, if not easier than the previous problems we've been working on. But remember, area is the length times the width for a rectangle. So we have the length, we have the width. All we have to do is multiply these two polynomials together, and you'll end up with 2x squared minus 9x minus 5. Let's now take a look at a triangular area. Remember, the area of a triangle is different. It's not length times width. What we have here is 1/2 times the length of the base times the length of the height. Okay, so you have these dimensions. Go ahead and give it a try, and we'll come back and see what you end up with. Okay, well, hopefully you were able to figure this problem out, and it wasn't too difficult, because again, all we're doing is we're multiplying the base and the height, the 3x plus 2 and the 2x minus 4 together. We ended up with the polynomial 6x squared minus 8x minus 8, and then we have to multiply this by a half. So when we distribute the half through to each thing, we end up with the 3x squared minus 4x and minus 4. And that's it. That's how we're doing these different geometric problems where the dimensions that we have are really polynomials. Hopefully this section's making sense to you and you're feeling more comfortable working with these unknown or variable quantities. But if you have any questions or comments, feel free to let me know. My email is klinford, that's KLINFORD, at wccnet.edu. Let me know what you thought of the video or if you have any questions or comments. And until next time, take care.